Welcome back to the details video about the A1335 precision Hall effect angle sensor. In the basics video, we've got two of those up and running using an existing library I found on the internet. Card here, link in the description. Then we had a little intermezzo where I built these Lego Technic test jigs for the sensors, basically allowing us to rotate two magnets in front of them with defined zero position detents and some friction here on the axis so we can really precisely set an angle. Card here, link in the description. In the basics video, I mentioned that I found the library we were using back then lacking in some respects. So in this video, we will start building our own library for the A1335. Enjoy! Like most I2C devices, or for that matter SPI devices, the A1335 is controlled by reading and writing a set of registers via the serial interface. However, the registers you can read and write here via the serial interface are all 16-bit, so that's something you don't find that often. And in addition, there is a block of registers here that you can use to read and write an extended set of registers, which are 64-bit. In this video, I will concentrate on the standard registers here and I will save the 64-bit stuff for a later time. Please note that this picture from the A1335 programming guide is incomplete. There is a register missing here and it contains at least one error. The mnemonic for the extended error mask register is just XERM, not EXERM. So we won't use this picture here in the following. Instead, I will be using the table 3 from the programming guide, the primary serial interface registers bits map. And as mentioned, I won't talk this time about these registers here for extended read and write operations, but concentrate on that block of registers down here. There we have a control register used to set the chip into run or idle mode, to perform a hard or soft reset, and to clear the different status and error registers. To perform these functions here, you set the bits, but for each bit you also have to upload a specific 8-bit key code, otherwise the function will not be executed. Did I mention this is an automotive grade chip? Then we have the angle register, which gives you, of course, the angle that has been measured, plus a few more flags, amongst them a general error flag indicating that some error happened, then a new flag indicating that the value you just read is actually a new value that has been measured, and a parity bit, automotive. That is followed by the status register, which starts with a 4-bit register identifier code. And all following registers have also a unique register identifier code. That's also an automotive grade thing to make sure if you read a register that you really read the register you wanted to read. Anyway, the status register just repeats some flags we already found here in the angle register, like a general error bit and the new data flag, but it also gives you detailed information about what the chip is doing. Is it running? Is it idle? Is it booting? Is it performing a self-test, etc. The error register also starts with its register identifier code, and then comes an extended error flag indicating that there is an extended error, and then come a whole lot of error flags. The extended error register, register identifier code, and even more error flags. Then we have the temperature sensor register, also starting with its register identifier code, and that gives you the temperature as it is measured by the internal temperature sensor, which is used, of course, for temperature compensation purposes. That is accompanied by the field register, register identifier code, and then the magnetic field strength that is measured. Finally, we have an arrow mask register with its register identifier code, which contains a bit mask for the arrow register, so you can mask out single arrows and prevent them from setting the general arrow flags in the status register and in the angle register. And the same holds true, of course, for the extended arrow mask register here. Please note that the most significant byte goes on serial communications first over the line and is followed by the least significant byte. Before we dive into the details of each and every register, let's cover some basics of the library. So I have here my A1335_I2C.h file, and it starts with the usual if not def define for a .h file. And then we include the Arduino.h, so the compiler understands all this Arduino specific stuff. And of course we need the wire library because we are using I2C. And then our class starts. The constructor of the class gets as an argument a 2-wire object and a byte I2C address, which of course should contain the I2C address of our chip. And then we have a Boolean begin, which returns false if anything should go awry. Here in the CPP file, we have the implementation of our constructor, and it really just initializes 2 private member variables with the arguments. We will talk about that Boolean begin a wee bit later. Back in the .h file, we have another public method, last library error, which returns the last library error we encountered. For example, if begin returns false. Library error is of course just an unscoped enum, and I'm using an unscoped enum here so we can use bit operations on these values. And we have here, for example, a block with all our 2-wire errors and then a block with bit errors. And I also provide here a bit mask to identify any 2-wire error using some bit operations. That's just a convenience thing. Down in the private section again, we find our 2 private member variables, 2-wire and I2C address, and also a library error, last library error, which of course holds the last library error that I encountered. Then we have 2 private functions here, Boolean read primary register, so it can fail, that gets a register address and a reference to some 16-bit register data, and write primary register, that also gets a register address but a constant reference to 16 bits of register data. In the CPP file, we of course find the implementation of the read primary register function, and I won't go into the details of I2C communication and general architecture of such a library. I've already done it in the details video about the QST QMC 5883L 3-axis digital compass. Card here, link in the description. Anyway, we get here our register address and we have here our register data. And I want to point out here at some point after I do all the I2C stuff, see the other video, I start swapping the bytes that I received via I2C when I read that register. The reason being, I told you the A1335 sends the most significant byte first. However, in the Arduino world, the least significant byte comes first. So you have to swap the bytes, and That's exactly what that line does here at the end, and I haven't had to do that with a QMC 5883L because that chip uses only 8 bits, single byte registers. And here we have our write primary register function, which works exactly as for the QMC 5883L, but writes 2 bytes. And in the beginning, I'm using here a little byte buffer variable to again swap the bytes into the correct order, so the A1335 will understand what I want to do. Now let's talk about the control register. So we have here 2 bits that can change the processor state. We have a hard reset bit, a soft reset bit, a clear status register bit, a clear extended error register bit, and a clear error register bit, and the aforementioned key code. To change the processor state, CDS, don't ask me why, we have to load hexadecimal 46 into the key code bits. And if we load 10 into the change processor state bits, we enter the idle mode, and if we load 11, we enter the run mode. Any other combination does nothing. To initiate a hard reset, we have to load hexadecimal B9 into the key code bits and then set the related hard reset bit. Analog for soft reset, we also have to load hexadecimal B9 into the key code field and set the related soft reset bit. To clear the status register, load hexadecimal 46 into the key code parameter. That's the same key code here for change processor state, and set the related bit. To clear the extended error register, again, it's the same. Load hexadecimal 46 into the key code, set the related bit, and please note, that only happens after reading the X error register. So, yeah, automotive stuff again. You cannot clear that extended error register unless you have read it beforehand. That leaves us with the clear error register bit, which works exactly the same. Load hexadecimal 46 into key code, set the bit, but don't forget to read the error register beforehand. And then, of course, we have our 8-bit key code. The library interface for that control register consists of 5 functions here in the .h file. So I have a hard reset, I have a soft reset, I have an idle mode, and I have a run mode, and I have a clear register which gets an argument here. We have a look at that in a second. All these functions can fail, of course, and then you use the last library error to retrieve the exact error that happened. Clear register is just another unscoped enum here, defining the 3 different bits for clearing the different registers. And of course, you can binary all these values here to clear several registers at once. In the private section of the class, I have a constant here for the register address and constants for all the other register addresses. Please note that there are quite considerable gaps here in the register addresses. These are all undocumented registers that you shouldn't use. Also in the private section, I have here some more constants with bits and masks defined for the control register. So these are the 4 bits here for change to idle, change to run, hard reset and soft reset. And down below here I have the 8-bit combinations for the key code for either a change or clear action or reset action. So hexadecimal 46, respectively hexadecimal B9. The other bits here in between for clear register we already defined in that enum. The implementation of the control register functions in the CPP file is mostly trivial. So for example, here we have the software set that simply defines a constant here, primary register control data, which consists of the soft reset bit logically ORed with the key code for the reset. And then I write that here using write primary register to the control register address, with the data I just defined here. The same holds true for run mode and for idle mode. Clear registers works a little bit different because I already get the bits for clearing registers here as an argument, so I don't have a constant here but instead a variable for the register data, and I fill that with the bits I get as an argument, and I binary all that with the key code for change or clear, and then I write the whole thing to the A1335. Hard reset is a different kind of beast. So I have here still, as before, my constant for the control register data consisting of the hard reset bit and the key code. But then I have here an extra local variable, a save last library error of the type library error, in which I save the current library error. Then I do my write operation to the A1335, and should that fail, I check first if the last library error was a library error to wire data not acknowledged. The thing here is, as soon as you start a hard reset, that is, the last bit of the hard reset pattern has been written to the control register, the chip starts with a hard reset and does not give you an acknowledge back on the I2C that really the last byte here has been written. So that's not really an error, not receiving an acknowledge signal here. That's just, the nature of the game. And by the way, that's not documented really in the programming guide. Anyway, if that should be the case, then I revert to the saved last library error, and otherwise, if some other error occurs, there was really something wrong and I return false. Now, what we've all been waiting for, the angle register. As mentioned before, it starts with a few flags, and the first flag is a register identifier, a code. It's really just a single bit, and that bit has to be 0. Please note the register identifier codes of all the other registers start with a 1. So you can make a distinction there. Then we have the error flag, which is set if there's any unmasked error bit set in the error register. Remember, the error register starts with an extended error flag, which in turn is set if there's any unmasked error bit set in the extended error register. So that error flag really catches any unmasked error or extended error. Next is the new flag, which is set to 1 if there is new data in the angle register which has never been read before. Finally, we have the parity bit for the angle register, and that's an odd parity of all other bit values in the register. So the sum of all values of the bits in the angle register, including the parity bit itself, has to be an odd number. The angle itself is a 12-bit value, so maximum value is 4095, and you can simply convert that into degrees by multiplying it with 360, maximum value, degrees on a circle, divided by 4096. Also, there's a function here that once you transmitted the address of the angle register, you can continuously read the 2 bytes of the angle register. So there's some looping, but I won't make any use of that at the moment. The interface to our angle register in the public part of our class consists of just 4 functions. I have here a read angle that really reads the register from the chip via I2C, and that can of course fail, and then you use last library error to retrieve the fault condition. Then I have an angle degree and angle raw that returns either the angle in degree or the 12-bit raw value of the angle. And finally I have a boolean angle new here that returns true if the angle new flag is set. The angle register I read from the chip is buffered here in a private variable, and I do the same for all other registers I'm actually reading from the chip. For the philosophy behind that and the architecture of the library, again refer to that QMC 5883L, the details 1 video, already carded, a link in the description. Of course, there's a whole bunch of bits and masks for the angle register here in the private section of the class defined as static constants, and we will use these now in the implementations of all our public functions. The implementation of the read angle function uses of course our private read primary register function here to read the register into that private member variable here. And if that fails, we return false right away. Please remember, read primary register already sets last library error to any I2C error we might have encountered. Then we calculate the parity here, and just Google for calculate parity bit and you get that kind of code. I'm not gonna explain that at this point. And if our parity doesn't check out, then we set last library error to library error bit angle parity and we return false. Yeah, something was wrong with our angle register. Also, we check here if the angle register identifier code bit, yeah, just 1 bit, is not 0. And if that's the case, then last library error is last library error bit register identifier code. Finally, we check if the primary register angle error flag is set, and if that's the case, so there is any unmasked error in our error register or extended error register, then we set last library error to library error angle error flag and we return false. Otherwise, we were successful. Angle degree uses first the angle raw function to get the 12-bit value, which is cast into a 32-bit unsigned integer and multiplied by 360. That cast is necessary because 4069 times 360 doesn't fit into a 16-bit integer. Then we cast the whole thing into a float and we divide that by 4096, which yield us the angle in degree. Angle raw is really just the binary AND of the content of the register and the bit mask for the 12-bit angle. And so angle new is really just the content of the register binary ANDed with the bit of the new flag. We actually need 2 more registers before we can really use the chip. And these are the error register and the extended error register. The error register starts with a real 4-bit register identifier code, and that has to be 1010. And all real register identifier codes start with a 1. Remember, the angle register identifier bit is a 0. That is followed by the extended error flag. I already mentioned that. This is set if any non-masked error is set in the extended error register. That is followed by 11 real error flags. The first being extended access error flag, which is set if you are doing extended read and write access to the 32-bit registers too fast. Then we have an interface error flag that is set if there's some problem with an SPI package. We don't care about that really. There is an CRC error flag if some parity error occurs on an SPI package, also not really of interest to us. Then we have, more interesting, not in run mode, which is set to 1 if the processor is idle. Then we have an angle processing error flag if the processor has any problems with producing new angle data. The angle high fault flag is set if a maximum angle that you can set in the extended registers is exceeded. Analog, the angle low fault flag is set if the angle falls below a certain limit you can set in the extended registers. There's an overvoltage fault flag, self-explanatory, as is the undervoltage fault flag. There is a magnetic sense high fault flag. The magnetic field is too strong, and the magnetic sense low fault flag that indicates that the magnetic field is too weak. And here are the public methods for the error register. So of course we have a read error register that can fail. Then we have a method or function error here that gets here a error flag bit array and tests if any of these bits are actually set, and then it returns true. Error here is just another unscoped enum, so you can use bit operations on it that defines all the error bits in the error register. Error just returns all the error bits set in the error register in an enum error here, if you want to bit bang yourself a bit. And then we have a whole bunch of error type function which just return a boolean yes or no if a certain error flag is set. And in the private section of the class, I have a whole bunch here of private constants that define first a bit mask for the 4-bit register identifier code, and then, amongst other things, the register identifier code for the error register, and of course all the other register identifier codes for the other registers. The implementation of all these methods in the CPP file is almost trivial. So read error uses a read primary register to read that register via I2C and to store it in our private buffer variable. Then we check if the register identifier code is correct. If that's not the case, we set last library error to last library error bit register identifier code, and we return false. Otherwise, everything was good and we return true. Error gets as an argument that bit mask here with the error flags, and it compares that bit mask with the content in our private variable, and if any bit matches, it returns true, otherwise false. Error just returns the content of our variable here, binary ended, with the complement of the register identifier mask. So it really just returns the error flags without the register identifier code. The rest of the functions, like for example error extended error, just makes a binary end of the related error flag with our private variable storing the value of the error register, and if the bit is set, it returns true, otherwise false. Okay, the last register for today, the extended error register, which of course starts with a 4-bit register identifier, which in this case is 1011. That is followed by an SRAM soft error flag. Remember, that thing really contains a little CPU with everything. Amongst other things, an EEPROM, so we also have an EEPROM soft error flag. And then we have an angel warning flag that just tells us that in one of the extended registers, the angel status register, there is a warning present. We also have a temperature sensor error flag just saying, okay, the temperature range has been exceeded. If soft errors for the SRAM and EEPROM, so recoverable errors, are detected, then of course the whole thing also detects hard errors on the SRAM and EEPROM, so irrecoverable errors, something is wrong with your chip. Then we have two watchdog error flags. Remember, that thing is automotive grade, so of course it contains a watchdog for the processor. The first one, watchdog processor halted fault flag, indicated that there was a watchdog timeout and the processor is indeed halted, so that was non-recoverable. Then we have the watchdog timer fault flag, which indicates also a timeout has occurred, but the processor might only be inactive. So it was tried to reset the CPU to get it up and running again. There is a reset condition flag that is simply set if there was a power up reset or a hard reset. An execution error flag indicating that reading or writing from the 32-bit registers, which can be SRAM or EEPROM, failed. A memory address error flag that indicates that we tried to read or write from an extended memory address that is not valid. And finally, a self-test failure flag. That thing does a self-test on power up or after a hard reset. If that fails, that thing here is set to 1. The public methods in our class for the extended error register work exactly the same like for the error register. So we have a read extended error function that does actually the reading of the register via I2C. We have an extended error function where you can pass a bit mask of extended errors, and if any of the error bits is set in the extended error data we just read here, then true is returned. We have extended error that returns a bit mask with all the extended errors that are set in the register. And finally, a whole bunch of functions to test single bits of the error register. And here is again the unscoped enum extended error defining all the error bits in the register. And yeah, the private stuff we've already seen, and I don't think we need to have a look at the implementation. It's really exactly the same like for the error register. With all that under our belt, we can finally have a look at the begin method. So first of all, we do a hard reset to get the A1335 into a defined state, and then we wait 500 microseconds, that's quite an arbitrary number, until the A1335 is up and running. Then all we want to do is to clear all our error registers and the status registers. Remember that error flag hard reset? Yeah, that is of course set here because we did a hard reset or because we just powered up the whole thing. And as long as that reset flag is set, that's an error, and so we got the general error flag set in the angle register. So as long as we don't clear all these registers, we always have an error when we try to read an angle. But before we can clear the registers, remember, we have at least to read the extended error register and the error register. Otherwise, we won't be able to clear those. Yeah. Now for a little test sketch. We include, of course, our library here, and then I have two constants with the I2C addresses of my left and my right A1335. We create two A1335 objects from the left and the right sensor, passing the Arduino wire object here and the I2C addresses, and then I have here a little flag begin error that I will be using in the setup where we first initialize our serial port so we can send some data to the serial monitor or serial plotter. Then we do a wire begin and we set the wire clock to 400 kilohertz fast mode. The chip is able to handle that. Our begin error is false, so we assume everything will be all right. We do a begin for our left chip. If that fails, we print the library error out that occurred. And a begin error is, of course, true then. We do the same for the right chip, and then we are finished with the setup. In the loop, we exit the loop if there was a begin error somewhere, then we wait 200 microseconds and then we read the left and the right angle sensor. And if something should be wrong, we print out the library error and then we print out to the serial port the angles we just read. Print library error is really trivial. It gets a little text string, which I'm passing here, so I know where the error occurred, and the I1335 library error. And yeah, I also print that out to the serial port. And yes, I catch that typo here. That was before left instead of right. And that's how the whole thing looks on the serial plotter. And if I turn a magnet here, yeah, nice. There's my 0. It's not quite 0 here on the scale, but we will cover that in another video. Yeah, works as expected. Very nice. And yeah, here's my 0 detent. And do you notice how there's almost no noise on the signal? That's very nice. That's a really nice sensor for you. Anyway, to be honest, that's about as far as we got in the basics video, already carded, link in the description. But now we do that with a, let's say, much more robust library. That's it for today. Next time we will cover the rest of the primary registers. Till then, bye!